this chapter, we will be exploring the calculus of trigonometry. In this lesson, we'll be looking at the derivatives of sine and cosine.
All right, hi everybody. So in this video here, we're going to take a look at the derivatives of sine and cosine. And if you've had any experience with trigonometry in the past year, you're probably aware, or you've come to the conclusion that most of the trig functions here can really be understood if you understood sine and cosine clearly. And that really is true here too. So we're gonna work on the derivatives of sine. Sorry, the derivative of sine in particular. Kind of generalize that, or at least you'll see the pattern, and I'll just give you the derivative for cosine because it's basically the same thing. And then I'm going to show you how you can get the derivative in a slightly different way, and I think you might like it. Okay, I kind of like the way the relationship works here. But anyway, so we're going to start off with, we're going to take the derivative of sine. So we're going to let our function here just be y equals the sine of x. Now, when we take a look at a brand new function and we're going to take the derivative, we got to go right back to first principles. So dy by dx is going to equal the limit as h approaches 0 of f of x plus h minus f of x all over 0. So there's our formula for finding the derivative. Okay, actually make sure that that's clear there. Minus f of x there. Now, we'll do a substitution. So this will be the limit as h approaches 0, or substitution, we'll plug in the function here. So this will now be the sine of x plus h minus the sine of x, and that's going to be all over h. Okay, now what do I do here? Well, I've got this x plus h here in the sine, and you should recognize that if you've done work with identities in the past here, that is going to be, okay, or at least that can be expanded by the sum and difference identity. So I can rewrite the sine of x plus h as the sine of x cosine of h plus the sine of h cosine of x minus the sine of x, and that's still all over h. Okay, so I really haven't done anything here. I just applied an identity to rewrite that sine of x plus h. No big deal. Okay, now what am I looking at here? Well, I've still got the limit as h approaches 0. I'm not even close to getting that dealt with yet. What have I got here? Well, I've got two terms that have a sine of x in them. That's, at the very least, let's move those together. So that's going to be the sine of x cosine of h minus the sine of x plus the sine of h cosine of x. And this is still all over h. Now, I know that I can distribute the h to every term in the numerator. The reason I bring that up, the reason I think that's significant is because right here I've got a sine of h. So I know that that sine of h over h, okay, if I let h go to 0, I know that that's going to go to 1. So I like that right there. I'm still not quite sure what to do with this. I do, however, have a common sine of x there. So what I'm going to do right now is I'm going to do two things in this particular step here. I can distribute the h, okay, because I've got these three terms here all being divided by h. I can kind of split that up, and I'm going to divide this pair of terms by h, then I'm going to divide this one by h here, and I'm also going to split up the limit here. So it's going to look like this. This will be the limit as h approaches 0 of the sine of x multiplied by the cosine of h minus 1 all over h plus the limit as h approaches 0 of the sine of h cosine of x over h. Okay, I like how that looks there because I can see my sine of h over h, and I know that that's going to equal 1. Okay, and remember way back when we were talking about limits, and you took the limit of the sum of some terms there, that the limit of the sum is the same as the sum of the limits. So I'm totally free to do that, to distribute that limit through. Okay, so now I've got two limits here, and I'm going to approach those sort of separately here. To start off with, I really do want to pull that fundamental trigonometric limit out of this. Now the sine of x isn't going to do it. In fact, you're going to see I'm going to do something with the sine of x here in just a moment here, but for right now I'm going to leave it right there. I've got h going to 0, okay, and I've got the sine of x. Well, this is not, I'm not going to be able to build the fundamental trigonometric limit out of that sine of x. I got to do something with this cosine of h minus 1. But I do notice something special about that cosine of h minus 1 here, okay? What I see here is I see a factor from a difference of squares. Okay, cosine of h plus minus 1, cosine of h plus 1. So what I'm going to do here is I'm going to actually multiply this by the cosine of h plus 1. Now, this is all over h multiplied by the cosine of h plus 1. So I've got cosine of h plus 1 divided by the cosine of h plus 1. So that's just going to be equal to 1. So I really haven't done anything. Plus, now I'm going to take the limit as h approaches 0, and I'm going to be just really clear on this. This is the sine of h over h, okay, multiplied by the cosine of x. And I can really think of it like that quite easily here, because the limit is as h approaches 0, and the cosine of x doesn't have an h in it, so it's not being affected by that limit at all. Okay, I'm going to come back to that in a second here. This will be the limit as h approaches 0. When I multiply that out, okay, I am going to get cosine squared of h minus 1 all over h. Well, that's right, h multiplied by the cosine of h plus 1. Sorry, I forgot about the denominator there. Okay, when you multiply that out, because that's those are binomial conjugates there, okay, I'm going to get this squared term minus the squared term. Now, the reason I like that so much is because, well, and you should recognize that, that is actually going to equal, or that's part of an identity here. Now, way back here, I know that this, as I take the limit as h goes to 0, sine of h over h is going to go to 1. And so I'm going to be left with the cosine of x back there. So that's great, that's dealt with. So I know that the derivative of my sine function is going to have something to do with a cosine of x. It's going to have a term that's got a cosine of x in it. Now I got to figure out what's going on here. So I still got a bit of a mess to clean up. But I know, again from a previous course, I know that the cosine of h minus 1, okay, is going to equal the negative sine squared of h. Okay? This is going to be multiplied by the all over h multiplied by the cosine of h plus 1, and then I've still got this plus cosine of x back there. Okay, now I am a fair bit happier here, and I'm going to show you why here. I'm going to separate things out here. Now, the sine of x here is not being affected by the limit. I could, in fact, pull that sine of x out in front of the limit and just multiply it by the limit here. But now what I've got is I've got this factor of negative 1, and then I've got a sine of h, sine of h. I'm really spreading this out here. Okay? I'm going to switch the order of my factors in the denominator. So cosine of h plus 1 multiplied by h. And then I've still got this cosine of x hanging out in the back. Now, from this step here, the previous one, or the one that I just did here, all I did was separate out the factors of the numerator. I haven't done much of anything here. But now I'm going to take the limit as h goes to 0. Okay? I have got that sine of h over h. So actually, let me take all of these things in stride here. So I've got this rational here. The limit is not going to affect the sine of x, not a big deal. So it's just going to say sine of x. It's also not going to affect the negative 1. But sine of h over h is going to become 1. The sine of h, as h goes to 0, without the h in the denominator, is actually going to be 0. We looked at that the other day when we looked at the trig functions themselves here. When h goes to 0, the cosine of h is going to go to 1, plus 1 is going to be 2, plus the cosine of x back here. So now look at that. This is incredible here, because basically everything gets dealt with. My denominator is a number that I'm totally fine with. Having a 2 down there is great. But I've got this 0 in the numerator that essentially cancels that whole term out, and what I'm left with is the cosine of x. That's it. That's the derivative of sine. Now, isn't that incredible? Okay, so the derivative of sine is cos. So therefore, we can make this conclusion that if y is equal to the sine of x, then y prime is equal to the cosine of x. Okay, now before I get into this and start talking about the derivative of cosine, I want to show you one other way that we could have approached this derivative and still got the same result here. Let me graph this for you. Okay, so what do we got here? I'll go down a little bit further here. So here's my coordinate plane. Let's say I'm going up again, up to 1, down to -1 here. And let's say that this is, I want to make sure that I do this well here. If I start here, no, I want to split this up a little bit. So I'm going to go like this. I'm going to make this pi over 3, then make this 2 pi over 3, over here, pi, or 3 pi over 3. This will be 4 pi over 3, 5 pi over 3, and then way over here will be 6 pi. Actually, I did that pretty good. I'm actually impressed that that worked out as nicely as it did. This will be negative pi over 3, and then come back to more negative 2 pi over 3. Now, so what that means is I've got my pi over 2 will be like right here. So my graph, my sine graph when I plot it, okay, was going to go here, halfway, 0.86, so somewhere up here, there, down, halfway, 0, negative halfway, down, -1, halfway, and there. And then if I walk this back a little bit, my graph's going to go just something like this. Okay? Oops, sorry, right there, and then down. Okay, so my sine graph would look something like this. There we go. Okay, I've done worse. Done better, but I've done worse. There we go. There's our sine graph. Now, what I want you to notice about this is that, well, let's back this up a little bit. When we take the derivative, what we're doing is we're coming up with the slope of the tangent line. So let's just graph what the derivative would look like based on what we're seeing right here. And the nice thing is this is a nice periodic function. It does the same thing over and over again. So the slope of the tangent is also going to repeat. So we've got this negative section hits 0, positive section goes up, hits 0, gets smaller, gets larger, hits 0. So let's just plot out what we see here. Right here, the slope of the tangent is 0. So our derivative would go through 0. Same thing is here. Same thing happens here. Okay? Now, you can't quite see that my red isn't quite dark enough here, but it's going to go through 0, there, and there. Now, the slope of the tangent line right here, the slope of the tangent line right there is going to be 1. Now, that's not quite clear from my graph, but if I was to have this maybe plotted by a computer, and it was scaled properly, yeah, you would see that the slope of that tangent line there is just going to be 1. The slope of the tangent line right here, the slope of this tangent line is going to be -1. Slope of this tangent line right here is going to also be -1. And the slope of this tangent line, whoopsie daisies, right there is going to be equal to +1. And that would be very, very clear if we had a really good graph. Now, what does that mean? Well, if I plot my tangent line, the slope of this line here, where x is equal to 0, is going to be 1. So my tangent line goes through there. In pi over 2 radians, it goes down to 0. Okay, so it's going to go down to here. And then in another pi over 2 radians, it's going to hit pi. And the slope here is -1, which means my derivative will go down here. Then we see that it comes back up, goes through 0. And then when we get out to 6 pi here, sorry, 6 pi, that should have been 6 pi over 3. Oh my gosh. that should have been 2 pi, 6 pi over 3, is going to go back up to 1 here. And so what my graph is going to end up doing is this. Okay? And if I work that back, it's going to look like this. And isn't that just the graph of cosine? Okay? So this right here is just the graph of the cosine of x. So we can even see it graphically here that the cosine function is the derivative of the sine function. Now, before we leave this, okay, and go on and start doing problems here, I want to take a look really quickly. What happens if I've got y is equal to the cosine of x? Okay. Now take a look at this. If you just take a quick look at the cosine graph here, and I'll try to make this as clear as possible. By the way, I can do this derivative here algebraically. That would not be a problem at all. But now that you've seen it happen graphically, you might be able to anticipate where this is going immediately. So notice that the slope of the tangent line to the cos curve is 0 right here. So my derivative is going to go through there. Oh, doesn't that kind of suggest a sine function? Okay. Except that the slope of the tangent right here is going to be -1. Okay, because it's dropping down. So when we get to this point right here, the y-coordinate is actually down here as opposed to going up. And then when we get to here, again, the slope of the tangent is 0, and when we get to here, the slope of the tangent is +1. So if you plot this out, it actually does this instead. And then it goes up to 1, and then it goes back down to 0 here. And take a look at this graph right here. This is going to be the derivative of the cosine. And notice that it's not sine exactly, it is in fact negative sine. So if we're working with y is equal to cosine, then the derivative is going to be the negative sine of x. Okay? Which is kind of neat. Now, I want to show you one other little thing here, really quickly before we leave this. And from this point on, we're really just going to do some applications. We're just going to take some derivatives here. But I want you to notice this. I think this is incredible here. Let's say we start with y is equal to the sine of x. Okay? Then y primed is equal to the cosine of x. We've already seen that. Now, if I take the second derivative of sine, that means taking the first derivative of cosine, and we just saw this, I showed you graphically, this is going to be the negative sine of x. But now let's take the third derivative, which means taking the derivative of the negative sine of x. Well, we don't need to really worry about the coefficient. That's very similar to the work that we've done before. We really just need to worry about the sine of x. So it's going to be the negative cosine of x. And if I take the fourth derivative, taking the derivative, again, we don't worry about the coefficient here. We'll deal with that in a second. The derivative of cosine is going to be negative sine. Another negative pops out, which is going to make that positive, and we're simply going to be left with the sine of x. And so notice how 4 derivatives later, we're right back to the original function. Okay, so there's this nice little loop in the derivatives that we take. Okay, that being said, okay, at this point in time, I want to remind you of something here. And this is one of those points here where if we had a little bit more time right now, or if I had more time right now, I would really go and explain this quite clearly here. But this is worth an investigation on your part here. The derivative, taking the derivative, okay, taking the derivative drops the degree of a function by 1. Taking the derivative of a function drops the degree by 1. So I'm just going to leave you with a quick question here before I go on and just do some problems here, because this is worth looking into. This is so neat. what's going on here if this is true? How is it that we're creating this loop of these four functions here with our derivative if the degree is supposed to drop by 1 every time we take the derivative? That's some pretty cool math. All right, now we're just going to take the derivatives of a bunch of different functions here. Okay, just to take a look at how that works when we're working with trigonometric functions here. So to start off with, we take a look at y equals the sine, in parentheses, of x squared. Now, notice this is going to be an example of the chain rule because we're going to take the derivative of the outside function and then work our way inside. So therefore, our derivative is going to be, well, we got to take the derivative of the sine first. The derivative of sine is cosine of the interior function. And then we move inside the parentheses there and take the derivative of x squared, which is just going to be 2x. And then now normally what we would do at this point here is we would rewrite this. Now, I probably should do this underneath here, but anyway, we would rewrite this as 2x cosine of x squared, just to bring that nice little 2x, those 2x factors out front there. It looks better that way. Okay? Now, compare that to this one. Sine squared of x. Now, in this case right here, once again, we're still going to have to apply the chain rule, but we got to make sure that we're clear on what is the outside function here. In this case, we might rewrite this as the sine of x all squared. So in this case, the exterior function is going to be that squared. So we would bring down the 2 multiplied by the inside function there, and now multiply that by the derivative of the inside function, that's sine of x, and the derivative of sine of x is the cosine of x. Now, if you left it here, if I'm like some of your teachers here, I would probably dock you a little bit because you're not quite done yet, or at least you would be smarter to take advantage of the fact that this is an identity. I know that this is the same as the sine of 2x. Now, you don't always have to do that. Please don't misunderstand here. It's just that this particular identity is really useful in this chapter. Okay, it's just this one probably more than a lot of the others is going to pop up, and particularly in applications, it's just so useful to know that one off the top of your head there. Okay, now let's take a look at another one here. So now we've got two trig functions multiplied together. So this is going to require the product rule. So here we go. So the derivative will be, well, the derivative of the first term. So the derivative of sine will be cos multiplied by the second term plus the derivative of the second term, which in this case is going to be negative sine. So this will be sine of x multiplied by the negative sine of x. Now I'm going to just write this underneath here because this is going to become the cosine squared of x minus the sine squared of x. Okay. Now here's another situation here where hopefully you recognize that particular pattern. That is another identity, and in fact, that is the cosine double angle identity. I can rewrite that as the cosine of 2x. Okay, so that's always handy to do here. You didn't have that kind of freedom in a lot of the previous chapters here in this course because we were working with polynomials, rationals, radicals, and whatnot. But now we've got these trig functions, and there's a lot of identities we can use to help simplify things a little bit. Even right here, there's one. Now I want to talk about this one here in just a second to describe what's going on here and why there's this plus 2 pi. But let's just take a look at it. This is going to require the chain rule once again. So the derivative of cosine will be negative sine, and then what's inside there won't change. So it's going to be 3x plus 2 pi. And then I would multiply by the derivative of what's inside, and that's just going to be positive 3. Because remember, 2 pi is a constant. So the derivative of the 2 pi is just going to be 0 here. Okay, so now I'm going to bring that 3 up front. So this will be negative 3 sine of 3x plus 2 pi. Now, I want to talk about what's going on here. Let's just think about what that graph would look like. If I've got Okay, if I've got my unit circle here, I don't know exactly what angle 3x is. Let's just say that it's out here someplace that this represents 3x. Okay, whatever. I don't know. But what I do know is that if I add 2 pi to that, I go all the way around the full circle, and that's going to be coterminal to just 3x. So in terms of the trigonometry, the sine of 3x and the sine of 3x plus 2 pi will be identical. Okay? That is the nature of a periodic function. And so therefore we can say here that our derivative is simply going to be negative 3 sine of 3x. I can ignore that plus 2 pi there. Okay. Really interesting property of periodic functions. Let's take a look at another one. Okay, so now here I got a couple things going on, and let's make sure that we see clearly what's happening with this one here. I've got the cosine cubed of the sine of x. Well, and again, you need to know what it means when that cube is right there, and what that means is that we've got this additional external function here. We are cubing the cosine of the sine. So therefore, when I take the derivative, I will once again apply the chain rule. And once again, I'm going to go from the outside in. So my external function is 3. So it's going to be 3 all of the inside squared. Now, multiplied by the derivative of what would be inside here. And now that's going to be, because it's cosine, is the next function I see. It's going to be negative. And I'll just pop that out front here. Negative sine of the sine of x. But I'm not done, because there's one more interior function that I got to get to. Well, technically, actually, there's 2 more, but the next step is going to be to take the derivative of the sine, which will be the cosine of x. And then what I would do at the very end here is I would take the derivative of the x, really the deepest function here, which is just going to be 1. And so that's what this answer would look like. And actually, there's really not much more I can do to this to clean that up, to make that look better, other than perhaps just putting it in order of like least complex to most complex, or whatever. I might write this as negative 3, let's say, cosine of x, multiplied by the sine of x, multiplied by the cosine squared of the sine of x. Or the other way around, doesn't really matter, but that's about the most you can do with that. Now let's take a look at one last question here. Sine of y minus the cosine of 2x equals 2xy. Now, notice in this case here, because of the y's in there, that this is going to be, this is going to require an implicit derivative here. But we don't approach that any differently than we would of any other implicit function here. So take a look at this. When I take the derivative of the sine of y, I consider that to be a set of brackets. So I take the derivative of the sine first. So that's going to be the cosine of y. And now I multiply by the derivative of y, which in this case is really just going to be the y prime, the derivative of y. Because I don't know what that's supposed to be, so I use that symbol to represent it. Now, here, I would make this, I've got this subtracting the cosine of 2x. Well, this requires the chain rule, but not an implicit derivative here. The derivative of cosine is going to be negative sine. There's a negative right there, so it's going to make this positive sine of 2x. And then multiply by the derivative of what's inside there, then derivative of 2x. Oh, the derivative of 2x is just 2. Shoot. I did not mean to write that x there. It's just 2. Will equal, now over here, I'm going to apply the product rule. I'll treat 2x as one function, y as the other function, so the derivative of 2x is just going to be 2 multiplied by y plus 2x multiplied by the derivative of y, which will give us y primed. Okay. Now, what I want to do here is I want to get the terms that have the y primed in them together. So I'm going to bring this term over here, and then I'll move the term that doesn't have the y primed in it over. So I'm going to get for myself here the cosine of y, y primed, minus 2x, y primed, will equal 2y minus, and I'm just going to bring that coefficient of 2 up front, 2 sine of 2x. Okay, so just brought this term over and then brought this term over. I will factor out the y primed out of the two terms here on the left. Okay, and I will get 2y minus 2 sine of 2x, and then I'll divide. So y primed will equal 2y minus 2 sine of 2x all over the cosine of y minus 2x. Okay, now you might be tempted to want to factor out that 2, and by all means you can, but it's not going to allow you to simplify anything. Okay, you're not going to be able to cancel that 2 out with anything. Same here, you might want to replace the sine of 2x with 2 sine x cos x. But again, you won't be able to do anything beyond that point there. So it's just as good to leave it like this right now. That would be the derivative of that particular function. So the whole point of these exercises here is really just to point out that when we take the derivative of trig functions that are a little bit more complicated than just your basic sine and cosine, the rules are all the same. Okay, all the rules, your product rule, quotient rule, chain rule, implicit differentiation, they all behave exactly the same. So I hope that makes sense. I hope that helps you understand these two basic derivatives, sine and cosine.